Okay, so today I will be teaching you about active filter. The reason is we have to go to this one. The thing is on last Friday, I see on the Zoom talking about left phone, and they teaching you about filter. Okay, and I don't know. We'll see. You guys get the time to do the left phone on the JFET right now. JFET we get only 3 circuit board working. Total only 4, but only 3 working. So I don't know. The other instructor will make the design, okay, on that. But the active filter here, that means you okay. Now, first thing, if you're looking into here, I try to bring you to try to remind you about a very, very basic and it must be memorized. Okay. On this one here, we call a time domain. You understand what that means for time domain? That means the signal vary with the time. Okay, so that can be second, millisecond, microsecond, the time. And you know that one is a sine wave, right? The sine wave, if you're looking on the oscilloscope is the time domain. Okay? So, if they asking you, can we measure the frequency on the oscilloscope? Who know the answer?
You
Yes or
cannot,
no?
no, you can't measure the frequency. You can only measure time. And through the formula, that's how you get the frequency.
Perfect. That means the answer will be, you have to make sure they can understand. For the own oscilloscope, then on the basic oscilloscope, you cannot measure directly frequency. Only thing you can measure will be measure the period. And after the period, you're using the formula F equals 1 over T to get the frequency. The thing of frequency will be measured directly from frequency domain, not time. However, depending on oscilloscope, like the scope, you're working in the left volt, you can measure the frequency, right? You set up measure frequency, they given you frequency. The thing is, that scope cost more money. Okay, so they're adding more function, giving you the answer. However, what I want to say, basically oscilloscope only measure the period. And if you want frequency, you're using F equals 1 over T. Okay? And another one. Now, that will be distant domain. That means they vary with the distance. Okay? And that's why they get a wavelength lambda equal V divide F, where V equal 3 times 10 power of 8 meter per second, and F will be in hertz. That means they're talking about the signal transmitted over the air. Okay? That will be in RF radio frequency.
V is velocity, right?
Right.
Okay, thank you.
Now, you see this signal here. Basically, you get this as sine wave. Okay? Sine wave, let's see, square wave is make up of fundamental sine wave and an infinite number of odd harmonic. Now, you get a sine wave here, and each sine wave, they can get a different frequency. Okay? That's what they're talking about, harmonic. Fundamental. This is a fundamental here. Okay? They're talking about harmonic, but odd harmonic. Third harmonic, this one. And the fifth harmonic, and so on. Okay? More harmonic, they make it up to the square wave. Okay? Now, if you're looking on that one, this is a time domain. You know square wave. You guys already know. Peak to peak voltage. Okay. What the period? Time domain oscilloscope. Sphere of 1 kilohertz square wave. That means frequency is 1K. However, if you display on the frequency domain, that means you're using the logic analyzer. They display the same signal. However, you can see what the difference. Frequency domain spectrum analyzer for 1 kilohertz square wave. So the first thing you can see, they display fundamental 1 kilohertz. Look like this one. Do not see a square wave or sine wave. They're telling you what the voltage peak, okay? And second thing, they will be third harmonic, another one with a different amplitude and so on. They keep display, okay? 7 harmonic, 9 harmonic, and so on. So you can see the difference, okay, between the square wave display on the oscilloscope and the square wave display on spectrum analyzer. Now, after you're done for Tech 1, you already know how to working it this one here. Okay? And when you get the time, you want to learn more about spectrum analyzer. Okay? We get the equipment. Okay? For you to exercise. You know this equipment, spectrum analyzer, how much it cost? 24,000. Okay? And scope on the 400 to 1,000, 2,000. However, last time I think I already bought at least 5 spectrum analyzer. Okay. I try to see what the program can do. Later on, maybe will be changing. Okay. That means we try to including on the spectrum analyzer when you're working in the lab. This is the same thing. 1 kilohertz square wave, 500 millivolt per division, 200 microsecond per division. That means the time domain. And also same thing signal. They will be displayed in the spectrum analyzer. Okay? So if you want to learn on the spectrum analyzer, that's very simple. You connect the same signal into the spectrum analyzer and you can see, okay, how they look like.
Hey, Mr. Pham,
Yeah.
just a real quick question. In your training and experience, is it either 11 or 13 harmonics that makes the square wave?
Okay. That means you understand it's a fundamental, third harmonic. Okay, first thing, 1 kilohertz, okay, square wave. Third harmonic will be what frequency? Right here, 3 kilohertz.
3 kilohertz is the third harmonic.
Right. The thing is they're not using even.
Right. So the harmonics start at like 1, 3, 5, 7, 9, 13,
Exactly. Keep
11,
going. Keep
right.
going. Okay, fifth harmonic, 7, and so on.
So my
However-
question,
However, yeah,
oh,
I
my
answered your question.
oh, go ahead.
However, they can go too many harmonic, but they recommend for technician, you work up to 13 harmonic, good enough.
To make a square wave.
Yeah, same thing. But, you can go more. 13 and 15 and 17, so on, right?
Right. But what I was asking Mr. Pham was, I'm saying, based on all the years you've been working in electronics, have you noticed like the square wave is kind of like a pure square wave when you get to either 11 or 13?
13.
13. Okay. Thank you.
They recommend. Normally, you can try to working up until 13 harmonic, that be fine.
Okay. Thank you.
Okay, now we're talking about filter. That means you're talking about communication. That the signal transmitted over the air. Like you listen in the radio, okay? AM, okay? FM or whatever. That's what they try to deal with the filter. Basically, you get a low pass filter, high pass filter, okay? And a band pass filter, band stop filter, not too many. Now, when you're looking for, when you're using your radio, you want to tune into your radio station, like 730 hertz, for example. Okay? That will be telling you when the signal transmitted over the air. So basically, what frequency you able to get. I given you example. First thing we're talking about low pass filter. Active filter is transistor or op-amp combined with passive RC, RLICL circuit. The active device provides voltage gain, and the passive device provides frequency selectivity. So basically, they want to build a filter. They can using transistor or op-amp, and also including passive. That means R, C, or RL, RCL circuit. And now you know active device. That means you can using inverting, non-inverting amplifier, okay? Or CE amplifier, CBC, CC, or JFET. That active device. And basically, they given you the gain, okay? And the passive device will be provide you for what frequency you want, okay? The four basic category: active filter, a low pass, high pass, band pass, or band stop filter. That's what they call a notch filter. First thing, we're talking about low pass. Low pass, that means the pass the signal at the low frequency. Okay? Ideal response, AV. You know what that means, AV, right? The gain in dB will be equal V out divided V in. If you're looking on that one here, they say 0 dB. So, you know, at this point here, what AV equal. We're not talking about 0 dB. Nobody understands much about decibel. We're talking about numerical value. So at that point, what AV equal?
Zero dB.
I know. I say I don't want to talking about dB. You are not familiar with the decibel. I'm talking about real number. When they say AV, that means voltage gain equal 0 dB. We don't want that. We want the value, numerical value.
You mean like zero?
Whatever, number. When they said 0 dB, I want to know what the equivalent to the numerical value.
Zero.
Come on, man. Who else?
That was a wild guess. I mean, that's the ideal situation you're talking about, right?
Yeah, that means indeed right here.
Yeah, it would be VO over VI.
Right. Here.
So there is no gain
Why you say no gain?
because um it says zero. Well, you said you don't want to talk about the dB, but it's 0 dB. I mean, there's no gain. Seems like it's an ideal situation. I don't know how to say it right.
No, that's why I said instead 0 dB. I don't want 0 dB. I want the value, numerical value. See, same thing here. The gain equal 0 dB. That means the gain equal what?
FC.
No.
You better tell us, Mr. Pham, which snow.
Yeah.
I don't think
Output over input.
Yeah, I know. But when you're looking at it, say 0 dB,
Right.
I don't care about dB. I care about numerical value.
So the 0.
No.
Oh, 1.
1.
Okay, tell us why it's 1.
Why it 1? The thing is, you take the 20 log of 1 equal how many dB?
zero.
Correct? Instead using dB, I don't want using dB. I want to be 1. That means V out equal V in. That means you not lost any signal. By the way, I also want, if I take 20 log 0.707, what you get in dB?
-3.
-3. The thing is, when you're learning in the theory, they're using the dB, but we not deal with the dB. Normally in the lab for communication, they're using the decibel. In the real thing, you have to deal with the numerical value. So instead you say 0 dB, and that will be equivalent to 1. Or -3 dB, you must be understand that equivalent to 0.707. Okay.
Yeah, I'm looking at the decibel handout to refresh my memory.
Okay, now the thing is the signal transmitted over the air. What the hell? Okay, the signal transmit over the air. Basically, you will like you tuning your radio. You're going from one station to the other station. Okay, so now when they jump from one station to the other station, different frequency. However, they have to get a limit to stop the frequency of one station and to a new one. If you're looking on that one here, they call it ideal. Never happened. Okay? No ideal response. That means very, very perfect output. And they get the FC. FC stands for cut off frequency. That's telling you the signal transmitted over here inside less than the cutoff. The signal cannot be changing. 5 volt peak to peak and still 5 volt peak to peak in and out. Okay, and that is the final. However, on reality, not happen that way. Now, you get cutoff frequency here. So the signal will be, okay, transmitted up to the cutoff. And after that, they want the signal will be going down. Okay? So in here, 0 dB, input, output will be the same. You not lost anything. However, at a certain point here, that's what they call a cutoff. So they will be lost minus 3 dB. Okay? I can give you the example here. Okay? You get a signal, okay, in here, 0 dB. Okay? You get 5 volt. So, at the cutoff, then now the signal will be how many? How many volt?
Oh, I think what you want us to say, Mr. Pham, is that you gave us 5 volts peak to peak, and you want to know what it is at the minus 3 dB point.
Exactly.
So then what you want is the square root of 2 divided by 2, which is actually 0.707 times 5 volts, and that's the answer.
Perfect. Okay. When they say minus 3 dB, okay, then you must know you get a 5 volt, and now they're going down 3 dB. You have to multiply, not minus 3 dB. We don't deal with the dB. Then you have to multiply with 0.707, whatever you get. That's why you can understand. At a 0 dB, you're coming in 5 volt. You're coming out 5 volt. The gain equal to 1. However, at the cutoff frequency, they say they're going down minus 3 dB. Then you want to know at that cutoff frequency what the amplitude signal. Then you have to take 5 times 0.707. And you know 0.707 equivalent to minus 3 dB.
So the voltage would have went down to 3.535.
Okay, 3.5.
Yep.
Okay.
Right.
If you don't know 0.707, then you cannot know what the value. I said if you can feel anything, just bring it up. Okay. Now, if you're looking into here, what they said, what slope? That means the amplitude going down equal minus 20 dB per decade. What that mean? When you're looking into the display, they said slope equal minus 20 dB per decade. How much you understand?
So you're saying a decade is 10, and then every it's 10 times the cutoff frequency, then the next one would be minus 40 dB.
Yeah, that's a different
Min-
story.
Oh, okay.
Right now, I just asking when they say slope equal minus 20 dB per decade, what that mean to you?
Every decade it's going down -2 dB.
20
20.
minus 20.
Every frequency is going -2 dB.
20 dB. You say it right here.
Yeah, but if the slope is going down and it's coming down at an angle right,
Right.
it would be coming down at a measured volume, you know?
Yeah, major volume, but they down. They down at the minus 20 dB
Oh, okay.
per decade. That means when you increment 10 times of the cutoff, like we already telling you, cut off 1K and 10 will be 10K, correct? That means at the frequency 1 kilohertz, you get the voltage here. However, when you try to go up to 10 kilohertz, they already going down, minus 20 dB. Okay, now tell me, minus 20 dB equals what?
Oh, I see these up here. Yeah. I somewhat remember, Mr. Pham. That's where you go like 0.001 or 0.01 or 0.1, and then you take the log and then time 20, and you
Okay,
get
now you can say you take a log of 0.707, you get minus 3 dB. And now I want it minus 20 dB.
0.1.
0.1. Okay. Now what that mean? 0.1, that means you get a 5 volt peak to peak, and now you're going down. 0.5, 0.1, right?
Right.
So 0.1 times 5, you get 0.5 volt. That means you lost, okay? The thing is when you're looking into that display here, you must really understand it. And that will be helping you for the rest of the filter. The same way. Now, one pole, low pass filter. Okay, so now you can get a 1 pole or 2 pole or 3 poles filter. 1 pole, what that mean? In the circuitry, you get 1 resistor and 1 capacitor. 1 pole. 2 resistor, 2 capacitor, 2 pole, and so on. Okay? Low pass filter only allow. Okay? Low frequency signal from 0 Hz to its cutoff frequency FC point to path Y, blocking those any higher. That will be telling you for this low pass here, the signal from here to here, they pass, and after that, they want to cut it off. This considered to be the noise, okay? So they want to cut it off. In the past, you're using the radio. Long time ago, when you're moving from one station to the other station, they make a lot of noise. Okay? The reason is they don't have a good filter. Good filter, that means after you get through FC here, they don't want any more signal. So that's why now your radio, you're moving from one station to the other, you didn't hear anything. The reason is they get a very, very good filter. After the cut off, they don't want anything else. They want to cut it off. Okay? Cutoff frequency or corner frequency or critical frequency, we already know. Cutoff frequency, the FC, they can be, say, cutoff frequency, or they say corner frequency, or they call critical frequency or stop frequency. Calculate by the formula FC equal to pi 1 over 2 pi times R times C, where F will be in Hertz, R ohm, C will be farad. Okay? At the cutoff frequency, the gain AV is down 3 dB, or the output going down 70.7%, same 0.707 of its maximum value. Okay? After the cutoff, output decrease at constant rate of the frequency increase. That is, when the frequency increase tenfold, 1 decade, the voltage gain is divided by 10. In other words, the gain decrease. Okay, 20 dB. You take 20 log of 10. Each time the frequency increase by 10. One pole low pass filter, 1R, 1C, roll off rate minus 20 dB per decade. But you want to know that equivalent to 0.1. Okay? If you get any question, okay, bring it up. I know I can answer you. If I don't, then will be and the answer to you later. Okay? No big deal. Two-pole low pass filter. The roll rate will be minus 40 dB per decade or 0.01. Three-pole, the roll off rate minus 60, 0.001. Basically, you want 3 pole. You don't want 1 pole. Why? You want after cut off. You don't want any more amplitude. Okay? That caused the noise problem. And now in here, they show you. Okay? 0 dB. That will be minus 60 dB per decade. 3 pole. 2 pole. 1 pole. Okay? Which one is the best? What I can say will be 3.
Mhm.
The thing is, after the cutoff, you don't want any more. Cut it off quickly. Okay? So now, they given you example. For the low pass circuit, R1K, G will be 101 microfarad. V in 10 volt IMS. They want to know the gain. You can see the answer that I already given to you. However, the gain they say equal to what? Why? Why the gain equal to 1?
Because the output and the input are the same. It's a unity.
Perfect. If you're looking into the amplifier, you have to know there is inverting amplifier, non-inverting, or follower, unity amplifier. You see the output connected directly to the negative. That means unity amplifier. Input, output will be the same. That's why the gain equal to 1. Okay? And now, they want to calculate the cutoff frequency. You know the formula. FC 1 over 2 pi. What I want to do, go ahead and calculate to telling me what I given to you, 1.59 kilohertz, correct or not correct. You have to do it, Okay? Okay, go ahead and calculate the cutoff frequency and verify for me, right or wrong.
Yeah, that's right. I get 1,591.549,431. So that's basically 1.59K.
Okay, who else? Mr. Smith be with me for a long, long time.
Hey, Mr. Pham, so they know all they do is just multiply 2 times pi times R. R is 1K times C, which is 0.1 microfarad, and then take the reciprocal and you'll get the 1.59.
Correct. But I want the other student. At
Okay.
least have to do calculation. I don't want to do everything for myself only, okay? If you're not doing it, you not really want to study, okay?
Mm-mm.
You get it? Make sure you can able to understand the basic for low pass filter. That will be no problem later. High pass filter or band pass filter, same thing.
Yeah, I don't know what type of calculator some people have, but I have like a Texas Instrument, and all you do is just punch in 2 times pi times R, which is 1,000 times C, which is 0.1 10 to the -6. Then you get an answer. Then you take that answer and take the reciprocal, and that's it.
Correct?
You can do it on your calculator without
Right.
doing anything else.
Right. Yeah, you take 2 times 3.142 times R 1,000, right?
Right,
1 times 10 power 3 times C 0.1 times 10 power minus 6.
right,
Then you just revert it, right?
right. Take the reciprocal once you get the answer.
Reciprocal. Right. Who else can verify for me? Is it 1.59 kilohertz? Why it take too long? Anyone else at 159? You can using your calculator. You can do everything. Okay, so basically you can see 1 over 2 pi equal what?
3.14.
3.14.
That's on the calculator as well.
142 times R will be 1 10 power of 3 times 0.1 times 10 minus 6. That's why you can get 1.59. Just using calculator. And also make sure you get along with your calculator. At work, sometimes you will need it. Okay? So anyway, I have to go. Number 3, they want to get the VR at FC. Now, telling me what the formula to calculate that. Okay? So you know at FC, then the output now will be V in time 0.707. So you get a 10 volt. That given you 7.07. And you calculate for me number 4 at 10 FC. They equal V in time what? First thing you have to find out 10 FC equivalent to what number?
0 dB.
You're using 20 log of minus 10, right? Oh, 10 dB. No.
What we can do is look at your graph there, Mr. Pham, where it's got the decades at, and it says 10 FC go all the way up to where you got 0 dB. But to get 0 dB, you have to take the log of 1, and that's 0, and 0 times 20 is 0. So the answer's got to be 1. Just looking at the graph.
Yeah. However, at the 10 FC
That's minus 20 dB.
minus 20 dB, right?
Right.
So equivalent to what a number? Like 0.707. You take the 20 log, they will be what? 3 dB, right?
3 dB. Yeah. Mhm.
Now, if they get 10 dB, so if you say you get 20 log, 0.1 equal what number?
Wait a minute, hold on.
Funny.
Is it
Yeah.
negative 20?
Yeah, it's negative 20, 0.1, and then you take
Okay.
the log, and you'll get a negative 1. And negative 1 times 20 is negative 20.
0.1 equivalent to minus, right?
Right.
So you're not using the dB. So you have to know what equivalent to that dB. So at 10 dB here, you can check the value will be 10 VIMS. You will be time 0.1. The thing is 0.1 equivalent to 10 dB. So that's why the answer will be 1. Okay, now this one. I just go to explain to you. I'm not going to detail. You do it. This is a low pass filter. You get R here, C here. Okay? However, what amplifier they're using? On the one we already done, they're using unity amplifier. Okay? Unity, gain is 1. Now on that one, what the name of the amplifier?
Unity amplifier.
What the name? You get inverting amplifier, non-inverting amplifier, unity gain amplifier.
Non-inverting.
Which one?
Non-inverting.
You say inverting?
Not inverting. Non-inverting.
Not inverting, correct. The input go to the positive, right?
Right.
That's not inverting. And the not inverting gain, okay, then you can say gain will be equal
to 10.
1 plus R2 over R1. That is the gain of the non-inverting. If you do calculation, answer will be 10. And now they want cutoff frequency. Okay, cutoff frequency, we already did it. FC equal 1 over 2 pi RC. VL maximum how come we get VL maximum? They will be take the input 2.5 volt IMS and you get the gain equal 10. So that's why you take the gain equal 10 times 2.5 VRMS, you get 25. Okay? And they can asking you VL FC. You know FC at 10 kilohertz, 10 times FC. 10 times FC equivalent to 0.1. Okay? So that's why you get 2.5. Okay? So you can try to do it. Otherwise, we don't have enough time. Active high pass filter. Low pass, they pass any signal lower than cutoff frequency. High pass, opposite. They pass signal higher than the cutoff frequency. Now, if you're looking here, okay, that will be telling you at this point right here, gain equal 1. That means any signal higher than cutoff, they will be passed. Any signal less than the cutoff, they will be the same. Okay, like the low pass. And if you go into the example, that will be helping you to understand. Only thing, when you're looking at the output here, you know that is the output of the high pass filter. That will be telling you any signal get a frequency higher than cut off, they let it go. It pass. However, less than, they will be cut it off. Just opposite to the low pass filter. Nothing else. This is just a calculation. Okay. And now I just quickly go over here. You're looking on this circuitry. We want to know what amplifier. The thing is, if you don't know the gain of amplifier, you cannot do any calculation. What is the gain of amplifier? What is the name also?
Well, it's inverting.
Perfect. That is inverted. That means you see the input go to negative, inverted. Okay, what is the gain?
R2 over R1
Minus, is it right?
minus R2 over R1.
Perfect. And the rest, you know how to do your calculation. And that will be helping you to calculate the gain. Okay, what is the VO maximum? That means you take the input times the gain. You know what is the maximum voltage. Okay. Cutoff frequency, you already know the formula. Okay. 1 over 2 pi RC. Okay. And also VO at cutoff frequency. Okay. That means you get a maximum voltage. You will be multiplied by 0.707. And then they can asking you, okay, at the cutoff 1.59 kilohertz. That means 10 times of FC. You know 10 times FC will be 0.1. You understand me? On the test final, I will be just asking you up to the point we're talking today. So basically, MOSFET or MOSFET amplified, don't need it. Okay? We'll be talking about that at the last day. Any problem on that one? Okay, if it's not, then we have to try to go. Okay? This is a true pole. That's why you can see you get to C, okay, and to R, true pole. You just understand true pole, they will be going down minus 40 dB. 3 pole, they're going down minus 60 dB per decade.
And Mr. Pham, real quick question.
Yeah,
So, say for one pole, C1 goes with R4 and C2 goes with R3. Is that correct?
you're talking about 1 pole or 2 pole.
The one you got on the screen right now. So C1 goes with R4 and C2 goes with R3. Is that how it goes?
That's what I think.
Okay. You understand what I'm saying, right?
Right, right. However, you don't have to do any calculation.
Right.
Even they already given the formula here. We don't want to make more complicated, okay? Only thing, sometimes you see the circuitry or myself also. It's hard to recognize 3-pole, 4-pole, okay? They have to tell you this is a 3-pole or 4-pole, okay?
And then on Mr. Bam, before you leave that one real quick, the gain is R4 over which resistor?
They're talking about this register here.
Oh, R2 over for the gain is R2 over R1 or how does it go?
Yeah, 1 plus, right?
Okay. Yeah, I
R2
see it
over
now.
R1.
I see it now. Okay, yeah.
The
Thank
thing
you.
is, this is a feedback register.
R4 looks like a feedback resistor too.
Now that going for filter.
Oh, for the filter. Yeah,
The thing is that
right.
is a positive,
right.
not a negative.
Yeah, that's right. That's the filter.
Okay, last one. Band pass filter. If you're looking here, you see this is high pass, right?
Right.
The thing is they pass high frequency. This one, low pass. They pass low frequency. Now they combine high pass to low pass. You make band pass. That means the signal will be passed at a frequency higher than FL and less than F high.
Okay.
So basically, band pass filter, they just combine high pass filter to the low pass filter. High pass, you get a one cut off. Low pass, you get another cut off frequency. So that's why in the band pass, you get 2 cut off. That means any signal get a frequency higher than F low and less than F high to pass, otherwise will be rejected. So you know most of the device in the RF they using band pass. Okay, later in cell phone, okay, they can using band pass filter. Okay, let's see. Band pass filter response. Pass frequency higher than F low and less than F high. This is the F low. This is the F high. Bandwidth equal F high minus F low. That's what they call a bandwidth. Okay. Quality Q will be equal F center. Here, center. Divide to bandwidth. Okay. That means how good the filter to be. Quality Q control the roll-off rate and the bandwidth of the filter. So when you see this signal, that normally when you interview job, they not giving you the circuit. Okay. The reason is very difficult to recognize the circuit. But they given you this one. They asking you, can you tell me what is it? Now, who can answer? If I interview, you guys interview with me, I just given you this one. Can you tell me what is it? Who can answer?
Well, you want the name of the filter?
Whatever you can say.
Well, the
I-
name of the filter is a band pass.
No, I'm not asking you about the gain. I just given you this signal. I just asking you what is it? Who can answer that?
A bandpass filter response?
Perfect. The answer will be, this is the output of the bandpass filter. Or bandpass filter response. Yeah, perfect answer. That's the only thing they want. And also you can tell him, okay, any signal with the frequency higher than F low and less than F high to pass. So that's why from F high to F low, they call a bandwidth, okay? And the signal outside, they reject it, okay? This is the circuitry, we don't care. Last one, band stop filter, or they call a notch filter. Same thing. Okay? Basically, they will be opposite to the band pass filter. That means any signal lower than F low, higher than F high, pass. Okay? The signal inside between F low, F high will be blocking. Just opposite. Okay? And this one, you can see they get a different, okay, filter. 1 pole, 2 pole, 3 pole, 4 pole. Basically, the bad will be this guy. 4 pole. Okay? The reason is they try to get a narrow band. Okay? Will be less noise. Okay? Now, by the way, if you're looking at the signal here, okay, you understand what is it here? What is it?
Sine wave?
Now, that one. Sideways, I agree. But you insist here, ripple. That means the noise. Okay. The noise admin unwanted signal. You don't want that signal. Okay. Basically, the signal you want will be here. See the line? Okay. So now, if you're looking into X1, this will be capacity elliptical, but the words best cell different type of the engineer design the filter. Which one you see is the best in this filter here? Tell me which one you prefer.
Bessel?
Yeah, if you're looking into a different filter. Okay, I know which one you think it is the best filter for your selection. Okay,
Either
now,
Bessel or Butterworth.
okay, you said the bottom word here, right? This guy, right? Okay, now, the best filter will be no noise. Second, cut off have to be very good by looking into the display, telling me. Okay, telling me which one. Okay, now, if you're looking on that one, not capacity, the thing is they get annoyed. Okay? Second thing, elliptical. This is elliptical. They get the noise. Okay? But the words, no noise. However, this is the cutoff. If you compare to best cell, then best cell will be better. Why? They don't have a noise. However, the cutoff will be better than but the word. Okay? So the selection will be best cell. Okay, any question, anything? Okay, that's just a formula. You can read that, okay? Okay, any question, anything? So, next week will be the final. You get 50 questions, 2 points for each. Take you around maximum 1 hour. So we will be start at 5:30. Okay? Any question, anything I can help? Make sure no class on Monday. Okay?
Okay, thank you.
You're welcome. Good night, everyone.
Thank you.
Okay? Take
Good
care.
night. Have a good weekend,
Thank you.
everybody.
Have a
Take
good
care.
night.
Thank you.